Variable frequency drives, or VFDs, control the speed of an electric motor by varying both the voltage and the frequency of the power supplied to the motor. When the motor is connected to a fixed voltage and frequency source, it operates at a constant speed. However, VFD use a variable voltage and variable frequency, or VVVF, technique to control the motor's speed. VFD reduce the voltage supplied to the motor as the frequency is decreased. This prevents excessive magnetic flux buildup, which could damage the motor. VFD vary the frequency of the power supplied to the motor. As the frequency decreases, the rotor speed also decreases. Maintaining a consistent ratio of voltage to frequency ensures that the motor operates efficiently and without overheating. Reducing both voltage and frequency simultaneously allows for a smooth and precise speed control of the motor. Some VFD include presets for specific speeds such as slow, normal, and fast. These presets simplify the operation of the motor by allowing the user to quickly switch between predefined speeds. Firstly, the VFD must be properly sized for the motor it is controlling. Secondly, the motor must be capable of operating at variable speeds and frequencies. Thirdly, proper installation and programming of the VFD is crucial for safe and efficient operation. To elaborate further on how VFD work, consider the following points. VFD are sophisticated electronic devices that provide precise control over the speed of alternating current, or AC, electric motors. They achieve this by manipulating the frequency and voltage of the power supplied to the motor. This allows for a wide range of speed adjustments, improved energy efficiency, and enhanced motor protection compared to traditional motor control methods. At the heart of a VFD is a three-part system: rectifier, DC bus, and inverter. The rectifier section converts incoming AC power to direct current, or DC, power. This is typically accomplished using diodes or thyristors. The DC bus section filters and stores the DC power, providing a stable voltage source for the inverter. Capacitors are commonly used in the DC bus to smooth out voltage fluctuations. The inverter section converts the DC power back to AC power, but at a variable frequency and voltage. This is achieved using insulated gate bipolar transistors, or IGBTs, which rapidly switch the DC voltage on and off to create a simulated AC waveform. By controlling the switching pattern of the IGBTs, the VFD can precisely adjust the frequency and voltage of the output power. The relationship between voltage and frequency is critical for maintaining optimal motor performance. As the frequency is reduced to decrease motor speed, the voltage must also be reduced proportionally. This ensures that the motor's magnetic flux remains constant, preventing overfluxing and potential damage to the motor. Overfluxing can lead to excessive heat generation and reduce motor lifespan. VFD use various control algorithms to maintain the correct voltage to frequency ratio. These algorithms constantly monitor the motor's operating conditions and adjust the output voltage accordingly. Some common control methods include volts per hertz control, sensor-less vector control, and field-oriented control. Volts per hertz control is the simplest method, maintaining a constant ratio between voltage and frequency. Sensor-less vector control provides improved performance by estimating the motor's torque and flux. Field-oriented control offers the highest level of performance by directly controlling the motor's torque and flux. VFD offers several advantages over traditional motor control methods. Firstly, energy savings. VFD can significantly reduce energy consumption by matching motor speed to the actual load requirements. This eliminates the need for throttling valves or mechanical dampers, which waste energy. Secondly, precise speed control. VFD provide precise and stepless speed control, allowing for optimized process performance. Thirdly, soft starting. VFD can gradually increase motor speed, reducing stress on mechanical components and minimizing inrush current. Fourthly, motor protection. VFD can protect motors from overvoltage, undervoltage, overcurrent, and overtemperature conditions. Fifthly, extended motor life. By reducing stress and providing protection, VFD can extend the lifespan of electric motors. VFD are used in a wide variety of applications, including pumps, fans, compressors, conveyors, and machine tools. They are commonly found in industries such as manufacturing, water treatment, HVAC, and oil and gas. When selecting a VFD, it is important to consider the following factors. Firstly, motor horsepower. The VFD must be sized appropriately for the motor it will be controlling. Secondly, voltage. The VFD must be compatible with the supply voltage. Thirdly, current. The VFD must be able to handle the motor's full load current. Fourthly, enclosure. The VFD enclosure must be suitable for the environment in which it will be installed. Fifthly, features. The VFD should have the necessary features for the specific application, such as communication interfaces, programmable logic controllers, and advanced control algorithms. Proper installation and programming are crucial for ensuring safe and efficient VFD operation. It is important to follow the manufacturer's instructions carefully and to consult with a qualified electrician or engineer. Regular maintenance is also essential for maintaining VFD performance and preventing downtime. This includes checking for loose connections, cleaning the cooling fans, and inspecting the capacitors. VFD are complex electronic devices, and troubleshooting them can be challenging. However, many VFD have built-in diagnostic tools that can help identify problems. It is also important to have a good understanding of VFD theory and operation. In summary, variable frequency drives are a versatile and effective means of controlling the speed of AC electric motors. By varying both the voltage and frequency of the power supplied to the motor, VFD provide precise speed control, improved energy efficiency, and enhanced motor protection. Proper selection, installation, and maintenance are essential for ensuring optimal VFD performance and reliability. Let's delve deeper into the components within a VFD, specifically the rectifier, DC bus, and inverter. The rectifier, as mentioned earlier, converts incoming AC power into DC power. This conversion process is crucial because the inverter stage requires a stable DC voltage to generate the variable frequency AC output. There are two primary types of rectifiers used in VFD: diode bridge rectifiers and active front-end rectifiers. Diode bridge rectifiers are the simpler and more common type. They consist of an arrangement of diodes that allow current to flow in only one direction, effectively converting the AC waveform into a pulsating DC waveform. The main advantage of diode bridge rectifiers is their simplicity and low cost. However, they also have some disadvantages, such as generating harmonic distortion in the input current and having a fixed DC voltage output. Active front-end rectifiers, on the other hand, use controlled switching devices, such as insulated gate bipolar transistors, or IGBTs, to actively shape the input current waveform and control the DC voltage. This allows for reduced harmonic distortion, improved power factor, and regenerative braking capabilities. However, active front-end rectifiers are more complex and expensive than diode bridge rectifiers. The DC bus section of a VFD plays a critical role in smoothing and stabilizing the DC voltage output from the rectifier. This is typically achieved using capacitors, which store electrical energy and release it when the voltage dips. The size and type of capacitors used in the DC bus are determined by the VFD power rating and the desired level of voltage smoothing. In addition to capacitors, some VFD may also include inductors in the DC bus to further filter out voltage ripple and improve stability. The inverter section of a VFD is responsible for converting the DC voltage from the DC bus back into AC voltage at a variable frequency and voltage. This is accomplished using a set of IGBTs which are rapidly switched on and off to create a simulated AC waveform. The switching pattern of the IGBTs is controlled by a sophisticated control algorithm that determines the output frequency and voltage. There are several different modulation techniques used to control the IGBTs in the inverter, including pulse width modulation, or PWM, space vector modulation, or SVM, and sinusoidal PWM, or SPWM. Pulse width modulation is the most common technique, where the width of the pulses determines the output voltage. Space vector modulation is a more advanced technique that provides improved harmonic performance and efficiency. Sinusoidal pulse width modulation aims to create a sinusoidal output waveform with minimal harmonic distortion. The control algorithms used in VFD are constantly evolving to improve performance, efficiency, and reliability. Some advanced control algorithms include sensorless vector control, field-oriented control, and direct torque control. Sensor-less vector control estimates the motor's torque and flux without the need for external sensors, providing improved performance compared to volts per hertz control. Field-oriented control directly controls the motor's torque and flux, providing the highest level of performance and dynamic response. Direct torque control directly controls the motor's torque by selecting the optimal voltage vector, resulting in fast torque response and reduced harmonic distortion. In addition to the main components, VFD also include various protection features to ensure safe and reliable operation. These protection features include overvoltage protection, undervoltage protection, overcurrent protection, overtemperature protection, short-circuit protection, and ground fault protection. Overvoltage protection prevents damage to the VFD from excessive voltage levels. Undervoltage protection protects the motor from running at low voltage conditions. Overcurrent protection limits the motor current to prevent overheating and damage. Overtemperature protection shuts down the VFD if the internal temperature exceeds a safe limit. Short-circuit protection protects the VFD from short circuits in the motor or wiring. Ground fault protection detects and interrupts ground faults to prevent electrical shock hazards. VFD also offer various communication interfaces, allowing them to be integrated into automation systems and monitored remotely. Common communication interfaces include Modbus, Ethernet, and Profibus. Modbus is a serial communication protocol commonly used in industrial applications. Ethernet allows for high-speed communication over a network. Profibus is a fieldbus protocol used for real-time communication in automation systems. In conclusion, variable frequency drives are complex and sophisticated electronic devices that provide precise control over the speed of AC electric motors. They consist of a rectifier, DC bus, and inverter, along with various control algorithms, protection features, and communication interfaces. Understanding the inner workings of a VFD is essential for selecting, installing, and maintaining them effectively. To further expand on the operational aspects of VFD, let's discuss specific parameters and settings that influence motor performance. One critical parameter is the acceleration time, which determines how quickly the VFD ramps up the motor speed from 0 to the desired operating speed. A shorter acceleration time allows for faster response, but it can also cause excessive stress on the motor and mechanical components. A longer acceleration time reduces stress, but it may result in slower process response. The optimal acceleration time depends on the application and the load characteristics. Similarly, the deceleration time determines how quickly the VFD ramps down the motor speed from the operating speed to 0. A shorter deceleration time provides faster stopping, but it can also cause regenerative braking, which can overload the VFD. A longer deceleration time reduces regenerative braking, but it may result in slower stopping. The optimal deceleration time depends on the application and the load characteristics. Another important parameter is the voltage to frequency ratio, also known as the volts per hertz ratio. This ratio determines the relationship between the output voltage and frequency of the VFD. Maintaining the correct voltage to frequency ratio is crucial for preventing overfluxing or underfluxing of the motor. Overfluxing can lead to excessive heat generation and reduce motor lifespan, while underfluxing can result in reduced torque and poor performance. The voltage to frequency ratio is typically set according to the motor's nameplate data. VFD also offer various torque control settings that allow for adjusting the motor's torque characteristics. These settings include torque boost, slip compensation, and current limiting. Torque boost increases the motor's torque at low speeds, improving starting performance. Slip compensation compensates for the motor's slip, maintaining constant speed under varying load conditions. Current limiting limits the motor current to prevent overheating and damage. In addition to these parameters, VFD also offer various protection settings to protect the motor and VFD from abnormal operating conditions. These settings include overvoltage trip, undervoltage trip, overcurrent trip, overtemperature trip, and ground fault trip. Overvoltage trip shuts down the VFD if the output voltage exceeds a safe limit. Undervoltage trip shuts down the VFD if the output voltage falls below a safe limit. Overcurrent trip shuts down the VFD if the output current exceeds a safe limit. Over-temperature trip shuts down the VFD if the internal temperature exceeds a safe limit. Ground fault trip shuts down the VFD if a ground fault is detected. Proper programming of the VFD is essential for ensuring optimal motor performance and protection. It is important to carefully review the motor's nameplate data and the VFD manual to set the appropriate parameters and protection settings. It is also recommended to consult with a qualified electrician or engineer to ensure proper installation and programming. Regular monitoring of the VFD operating parameters is also important for detecting potential problems and preventing downtime. This can be done using the VFD built-in display or through a remote monitoring system. Common operating parameters to monitor include output voltage, output current, output frequency, motor speed, and VFD temperature. By understanding the various parameters and settings of a VFD, users can optimize motor performance, improve energy efficiency, and enhance motor protection. Careful programming and regular monitoring are essential for ensuring reliable and efficient VFD operation. Let's further elaborate on the practical aspects of selecting and applying variable frequency drives in various industrial scenarios. When choosing a VFD for a specific application, it is important to consider several factors, including the motor's horsepower rating, the supply voltage, the load characteristics, and the environmental conditions. The motor's horsepower rating determines the size of the VFD required. The VFD must be sized appropriately to handle the motor's full load current without overheating or overloading. It is generally recommended to select a VFD with a horsepower rating that is equal to or slightly greater than the motor's horsepower rating. The supply voltage must match the VFD input voltage requirements. VFD are available in various voltage ratings, including 208 volts, 240 volts, 480 volts, and 600 volts. It is important to select a VFD that is compatible with the available supply voltage. The load characteristics play a significant role in determining the type of VFD required. Constant torque loads, such as conveyors and positive displacement pumps, require a VFD that can provide constant torque throughout the speed range. Variable torque loads, such as centrifugal fans and pumps, require a VFD that can provide variable torque as the speed changes. The environmental conditions, such as temperature, humidity, and dust, must be considered when selecting a VFD enclosure. VFD enclosures are available in various protection ratings such as NEMA 1, NEMA 3R, NEMA 4, and NEMA 12. NEMA 1 enclosures are suitable for indoor environments with minimal dust and moisture. NEMA 3R enclosures are suitable for outdoor environments with rain and snow. NEMA 4 enclosures are suitable for wet environments with splashing water. NEMA 12 enclosures are suitable for industrial environments with dust, oil, and non-corrosive liquids. Once the VFD has been selected, it is important to install it properly according to the manufacturer's instructions. This includes wiring the VFD to the motor and the power supply, as well as grounding the VFD properly. It is also important to provide adequate ventilation for the VFD to prevent overheating. After the VFD has been installed, it must be programmed according to the application requirements. This includes setting the motor parameters, the acceleration and deceleration times, the voltage to frequency ratio, and the protection settings. It is important to carefully review the motor's nameplate data and the VFD manual to set the appropriate parameters and protection settings. VFD are commonly used in a wide range of industrial applications, including pumping systems, 8-track systems, and conveyor systems. In pumping systems, VFD are used to control the speed of the pump motor, allowing for precise flow control and energy savings. By adjusting the pump speed to match the demand, VFD can eliminate the need for throttling valves, which waste energy. In 8-track systems, VFD are used to control the speed of the fan motor, allowing for precise temperature control and energy savings. By adjusting the fan speed to match the demand, VFD can eliminate the need for dampers, which waste energy. In conveyor systems, VFD are used to control the speed of the conveyor motor, allowing for precise material handling and process control. By adjusting the conveyor speed to match the demand, VFD can optimize throughput and reduce material waste. In addition to these applications, VFD are also used in a variety of other industrial processes such as mixing, grinding, and cutting. By providing precise speed control, VFD can improve process efficiency, reduce energy consumption, and enhance product quality. Regular maintenance is essential for ensuring reliable and efficient VFD operation. This includes checking for loose connections, cleaning the cooling fans, and inspecting the capacitors. It is also important to monitor the VFD operating parameters regularly to detect potential problems and prevent downtime. By following these guidelines, users can effectively select, install, and maintain VFD for a wide range of industrial applications.